this first picture that I'm starting with was taken when I went skiing, but that's not actually what I'm going to talk about. Instead, what I want to talk about is basically this question: what does your programming language need? And the answer that I will give in the talk is 3 functions at most. But before I go into this, I want to say a few words about myself. I'm a medical doctor by training, and I work in clinical research. So all of the things I'm talking about here, like Rust, functional programming, and maths, are just hobbies for me. I don't have any formal education or professional background in this, so take it all with a pinch of salt. And I also like skiing, but that's not the kind of skiing that I want to talk about. Instead, what I want to talk about is a little side project that I've been working on in Rust, which is to write an interpreter for the SKI combinator calculus. So it's usually pronounced SKI, but I pronounce it ski because it's more fun and it's shorter as well. So what is ski? So the SKI combinator calculus is, this is what Wikipedia says about it. The SKI combinator calculus is a combinatory logic system and a computational system. It can be thought of as a computer programming language, though it is not convenient for writing software. Instead, it is important in the mathematical theory of algorithms because it is an extremely simple Turing-complete language. And these highlighted words are going to come up a bit throughout the talk. So it's not a programming language, but rather it lives in a branch of maths called combinatory logic. Combinatory logic was introduced in the 1920s by these 2 people, Moses Schoenfinkel and Haskell Curry. And Haskell Curry is the person that the Haskell programming language is named after, and also a technique that the functional programmers might know called currying is named after him. So that already suggests that his work was very important in the foundations of functional programming. But originally, the combinatory logic system was not developed with a view to programming. This is the 1920s, so before the invention of modern computers. And it was initially introduced in maths as a way of removing variables from predicate logic, especially quantified variables, so something like for all or they exist. And the way that Moses Schoenfinkel originally came up with to remove the variables was by using something called combinators. So a combinator is a special type of function that doesn't have any free variables, which this is a bit jargony. This is not usually used so much, the term free variables, I guess, in programming. It basically means it only operates on its formal parameters and doesn't depend on any external state, and it doesn't capture any variables from the environment, and it doesn't have any side effects. And also combinators are higher order functions, so they take functions or other combinators usually as arguments, and they return combinators as well. And this idea of higher order functions is also something that is very important in functional programming. So there's a link here as well. So to give a few examples in Rust syntax, this first function ID takes an argument x and just returns it. That is a combinator. The second one, which I called const with a K because const with a C is a keyword in Rust, it takes 2 arguments and returns the first, and discards the second. The third example here takes an integer and adds a constant to it that, as the name suggests already, is not a combinator because it uses this constant that is defined outside of the function. And the last one, the last example here, it takes an integer and adds 1 to it. Strictly speaking, this is also not a combinator because we haven't defined plus and we haven't defined 1. However, we could define both of these as combinators as well, and then in that case, this would be valid, but as it stands, it's not really a combinator. So the SKI system in particular, or SKI system, uses these three combinators called SK and I, and only those. And the first one, I just takes an argument and returns it. That is the first example on the previous slide. And then K takes two arguments, returns the first, discards the second. That is the second example on the previous slide. And then S is slightly more complicated. It takes three arguments, applies the first to the third, and then the second to the third, and then it applies the result of the first computation to the second computation. So this is all there is in the SKI system. We only have these three functions, and one of them is not even strictly necessary. The I can actually be expressed in terms of S and K, so this is just syntactic sugar for SKK. You could, if you understand the rules, you could verify this yourself. So we have in the system only these three combinators. So all the arguments that we apply them to is also one of these three combinators. So they're higher order functions. They take other combinators as inputs and return combinators. Usually we evaluate it from left to right, and we only need to put parentheses if we want to change the order of evaluation. And we can compose them and return a new combinator as a composition of two or more of them. This is also the function composition is also something that comes up in functional programming a lot. And we also have the ability to partially apply them, which means I supply them with fewer than their required number of arguments, and then we return a new combinator which takes the rest of the arguments. Okay, so far it seems very simple, the system, and that we could do anything with it. It sounds kind of ridiculous. So I want to show you an example of actually doing computation in the system by doing Booleans. And now, of course, we don't have in the system true, we don't have false, we don't have and or anything like that. We only have SK and I. So I have to express all of these concepts by using some combination of SK and I. And there are potentially many that would work, but I'm going to suggest that we represent true SK and false SKI. And then I'm going to show you that we can represent and or A and B as AB false, or in other words, ABKI, then in our representation. And I will show you that this works by going through this truth table. So the first line, when A is true and B is true, we expect true and true to be true. So we look at what we get if we encode this in the SKI system. So AB false, that in this case translates to KKKI. In this case, the parentheses are required because we want to evaluate this portion first. We know that K takes two arguments and returns the first, which in this case is K, and we discard the second one. So the result of this is K, which is our encoding for true. So this checks out with the truth table. The second line, true and false, we expect that to be false. So we now write this as K, Ki, Ki. Again, we evaluate it from left to right. K returns the first argument, which is Ki, and this is our encoding for false. So this also checks out. The third line, false and true, we expect that also to be false. We write that as Ki, Ki. I could have put parentheses around the first Ki here, but it's not necessary because we're evaluating it from left to right anyway. So in this case, the K returns I and discards this K after it. And so in the next step, we have here I, Ki, and I, we know, just returns its argument, so that returns Ki. And this is false as we were expecting. And then the last line, false and false, should also be false. And when we go through this, again, here, ki, we first return I and discard this first ki, and then we have again iki, which returns ki, and this is false. So this is how you would do computations in the system. Whenever you want to use something that is not sk or I, you have to find a representation of it. The same you would have to do with numbers if you wanted to do addition or something like that. Here, this is an explanation why this works, why this particular representation of AND works. So you could think about this Rust function here, or you could think about defining AND, A and B, as if A, B, else false. And this first, the if branch, if A is true, this corresponds to the K because, we have encoded true as K. So if A is true, we are expecting to go into this if branch and returning B. And the K, we know that K returns the first of its two arguments, which in our representation here, if A is true, then the first argument of it is B. So this is the same as the if branch here. On the other hand, if A is false, we represent it as Ki. And this is equivalent to going in this else branch, because that the else branch is what we execute if A is false. And Ki returns the second argument. If you see Ki as an entire combinator, then it returns the second of its two arguments. This is not quite as immediately obvious, but if you look at what it does here, so Ki, you could also say Ki takes one argument and always returns I, discards the argument. And therefore, if you have another argument, you then have I and the second argument. And so this just returns the second argument, which in our case is false, because if A is Ki, then B is the first argument, false is the second argument. So this is equivalent to this else branch here. So this is the deeper meaning behind why this type of representation works and how it actually works. We could do the same for OR, but I'm not going to go through this in the interest of time now, because I want to get to some other things as well. So now we know we can do Booleans. We could also find something for not and XOR. But of course, this is still a long shot to claim that this is a Turing complete system. By Turing complete, this in general, this idea, it was introduced in the 1930s by this famous person, Alan Turing. And he came up with the Turing machine. He didn't call it that, but we now call it a Turing machine, which is a theoretical description of a machine that does computations. And it kind of represents of what it means to solve something by an algorithm. And at the time, there was another very different idea around as well, the lambda calculus, which Alonzo Church invented. And Turing then found that these two ideas are equivalent. And so he basically showed that the lambda calculus is Turing complete. Interestingly, Alonzo Church, who came up with the lambda calculus, was also Alan Turing's PhD supervisor. So I'm not going to show how you prove that the SKI calculus is Turing complete, but I want to give you the idea of what you would do to prove it. So first, you go and learn the lambda calculus. Then you find a way to reduce the lambda calculus to the SKI calculus. So you find a representation for everything that you can express in the lambda calculus. You find a representation in the SKI calculus. And by that, you have proven that the SKI system is at least as powerful as the lambda calculus. And then you are actually finished, because Turing has already proven that lambda calculus is Turing complete. So by extension, then the SKI system is also Turing complete. So now I want to shift gears and finally talk about interpreters. Because the whole idea of the project was to write an interpreter for the SKI system. And by an interpreter, a very simple view, I mean, so it has a lexer, which turns a string in the source code into tokens. Then the parser turns these tokens into a tree-like representation called an abstract syntax tree. And from there on, a lot of things could happen. Possibly, I chose probably the simplest one, but not necessarily a very efficient idea, which is to just traverse the tree and produce some output. So specifically for the SKI system, an interpreter would take in a string or some sequence of S's, K's, and I's, and then tokenize them somehow. That's not terribly important here. Then you want to parse it into an abstract syntax tree that looks a little bit like what I've tried to draw here. There are also probably different possibilities. In this case, the tree basically represents always the left child of any node is applied to the right child. And then at the end, this tree is being traversed, and we produce an output, which is also still a string in the SKI system, but potentially a simpler string, ideally the simplest possible, so that string that can no further be reduced. So I don't want to show the entire code, but I want to show one particular aspect of it, which is how we represent how I chose to represent the abstract syntax tree. So if this is like a picture of the tree in Haskell, I would quite literally translate that into a data type called ski, and this can be either an S or a K or an I or an application of a ski to another ski. And I think this is pretty descriptive, but how do we do that in Rust? So first attempt, let's use an enum. So again, we have here the possibility of saying this is either S or K or I or an application. I've factored this out into a struct, which has the combinator that you want to apply as one field, and another field, the argument that we want to apply it to. And yeah, and this is in here. But this doesn't actually compile in Rust because, well, it tells us why. Recursive types have infinite size, so this doesn't work. And the reason this doesn't work is that Rust needs to know how much memory to allocate for this. And it figures this out by determining which of the variants has the largest memory requirements, which in this case is obviously this application variant. And how much space does it need? Well, actually, what is inside it is this struct, which has another whole version of the ski. And then inside that, or actually two, and inside those, there could potentially be another whole version of it, and then another, and then another. So this could actually be infinite in size. So helpfully, the compiler already tells us how we can solve this. It says insert some indirection. And what it means is we are supposed to use a smart pointer. And so I chose the box smart pointer here. And now the size of this is simple. This is just the size of the pointer. And the actual data is allocated on the heap now. So this all compiles fine now. And that's actually all I wanted to say. Thank you for listening, and thank you for inviting me to speak here, Caroline, and thanks for organizing. And I think I'm going to stop sharing so I can see you again.
Thank you so much. That was really great. I'm realizing how little calculus I know. So yeah, it's I really appreciated the differences between Haskell and Rust there. That was a very good way of explaining it. I've heard Haskell is quite it can be quite expressive, but it's also really different to other languages. So it was kind of good to see a side-by-side comparison. Does anyone have any questions? And feel free to put them in the chat if you don't want to say them out loud.
I was just curious, how often do you use Haskell, Annika?
Yeah, I mean,
because it sounds difficult. I don't think I could honestly write in it, if I'm being honest.
Well, I mean, I don't use it professionally, so I only use it occasionally for spare time things. The same as Rust, I don't use that professionally either. So, yeah, how often? I don't know. Once a week or so.
That's a lot.
What do you use professionally?
Well, I'm not a developer. As I said, I'm a researcher. I do some coding or mostly data analysis, and it's usually Python. Occasionally R for some more advanced statistics where there don't yet exist dedicated packages in Python, but usually Python.
Do you think you could start using Rust at your work? Because just using a lot of data, do you think Rust would be good? Or is it just like at your work you can't use Rust yet?
No, we don't, although some people are interested in it at work. So there might be some idea of using it. I mean, other people in the company, the software developers at the company use Scala.
Oh, okay, gotcha.
But the data scientists use Python.
And R, which makes me sad. So
well, not really, but yeah, but yeah, it's
I have any excuse for me to like just rip on R is just an open for me. I absolutely hate it. But Giza, do you have a question?
Yeah, I think it's quicker to ask sort of live them in the chat. I was wondering, the code that you showed, was that sort of all for the ski calculus that you sort of more or less needed to then just feed it any kinds of computations, sort of the type definitions that you showed in the end and the functions in the beginning?
Well, I mean, I needed some other code for things like the parser and the evaluation, but for just representing the types, it's just that, and then the error types, because obviously you want to be able to represent if someone enters something that is not a valid SKI expression, like it doesn't contain just SSKs and I's, or it has unclosed parentheses or something like that. Yeah, so these types, then the error type, and then of course, yeah, some code for the. I separated out the Lexa as well, although it's not terribly exciting in with such a simple syntax. Then the parser and the evaluator.
Cool. How did you first come across Rust? Like right in the beginning, what was the?
Sorry, I missed the first.
What? How did you come across Rust in the beginning?
Oh, that's a good question. I don't remember exactly. Someone mentioned it in some. I think someone that I know who was also a Haskell programmer mentioned it at some point, and then I heard it mentioned a lot in like blog posts or so by people who are active in the Haskell community. There are quite a lot of people who are sort of a little bit famous in the Haskell community who also use Rust. I mean, as far as famous goes for the Haskell community.
That's great. And you've got a question. Have you open sourced the interpreter somewhere?
Yeah, so it's on GitHub. I mean, could probably share it in the chat or something.
Yeah, that'd be great.
Yeah, a lot of it is probably pretty crap.
There's no shame here. I think it was a really good use. I was wondering how you're going to represent it in Rust and say, and then when I saw it, I was like, oh, of course, an enum. That's definitely like the way to do it. But yeah, that's right.
Oh, now I have to get back to the meeting. Right? I'll just put a link in there.
Has anyone got any other questions before we turn the recording off?